to the final talk from this session. I think we have Scott Moore, who's going to tell us about synthesizing evidence of emergent computation. Scott, we can see you. This is good.
And we can see the slides.
And we can hear you. You're all good to go.
Great. All right, so thanks for the introduction. I'm going to be talking about a project and tool called SEEK, or Synthesizing Evidence of Emergent Computation, that I've been developing with some colleagues at Galois. So the goal of SEEK is to implement a tool that automatically finds counterexamples to secure compilation. And so before I talk about how it works and what we've done with it, I want to talk about some of our motivations for developing it. And there's 3 of them, and they're aimed at different use cases. So the first is that as many of you who are attending would and work on secure compiler design would know, they're really hard to get right. So one of our motivations is to help you test your design before you go through all of the effort that would be required to actually prove it secure. Our second motivation is that we know that all of the practical compilers we use today, in regular software development, are not secure in any general sense. But we don't really have good tools to explore for what programs or environments they actually do provide security, or how their insecurity manifests in practice. And finally, we're interested in using the ideas behind secure compilation to study system security more generally. It actually turns out that secure compilation is a really good framework for reasoning about the expected and unexpected behaviors of any interactive system. And so I want to expand on this point a little. So this is an idea we actually explored in a paper we presented at PriSC'22, where we argued that secure compilation is a great way to characterize what it means to exploit any system. So in that work, we tried to understand an informal idea from the hacking community that characterizes exploitation as a practice of programming a weird machine of unintended behaviors that can be triggered by providing unexpected inputs to a system. And sometimes these weird machines are quite literally something you could think of as a programmable machine. So you might have seen a recent Project Zero blog post detailing the exploitation techniques used in the Pegasus malware. One of the cool details about this is they actually implemented a full virtual machine using memory corruption vulnerabilities within a bitmap decoder. And so we like to think of these weird behaviors or emergent computations as evidence of insecure compilation. These are program behaviors that are not present in the design or high-level implementation of a system, but that can be triggered in its concrete realization. And so we built SEEK largely as a way to try and detect and understand the structure of these behaviors and identify ways to improve the security of both compilers and system implementations. So we realized this framework using a pretty standard definition of secure compilation, where we consider the relationship between the behaviors of a high-level model and a low-level model of a system that are related by a compiler, or when we're thinking about a design and its realization instead, a refinement relation. And I'm not going to go into the details for now, because it all gets a bit technical. So the SEEK tool, which we've open sourced on GitHub, is a framework for modeling systems and generating evidence of their insecurity. It consists of a domain-specific language for creating executable models of systems or compilers by implementing interpreters over language grammars, and also has a set of queries that can be used to identify different evidence of insecurity in those models. We built SEEK on top of the Rosette symbolic execution framework, which allows SEEK to symbolically execute the user's models and synthesize interesting interactions using its built-in counterexample guided inductive synthesis capabilities. So the workflow of SEEK is actually pretty straightforward. So to start with, a system or compiler designer is going to start by writing executable models of their source and target languages and the compiler or refinement relation between them. Then, using seek queries, the user can ask the system whether their model satisfies different secure compilation requirements. If the system or compiler is not secure, seek is going to generate counterexamples. The user can then use those counterexamples to understand what went wrong and refine their models by either fixing the compiler or the implementation, or modifying the specification of the relationship between the source and target behaviors to better reflect the threat model that they're concerned about. And then the user can continue repeating this cycle until seek reports that there's no evidence of insecurity that can be found up to the maximum size of interaction explored by the tool. And at this point, they may have some assurances about the quality of their design and what latent vulnerabilities might exist. So using seek, you can synthesize evidence of emergent computations at varying levels of complexity. So starting with just any example of a program and context that allow unexpected behaviors, all the way up to a collection of composable gadgets that could allow an adversary to perform whatever computations they desire. And I'm going to go into examples of these different levels of evidence in a minute in the talk. Intuitively, these higher levels of evidence are going to correspond to what we might think of as more dangerous kinds of insecurity, because they typically reflect that an adversary who triggers some unexpected behaviors is going to have more control over its effect. So I'm going to demonstrate how you use seek with a simple running example, which is the design of an API for manipulating a set of integers. And you can imagine specifications or implementations of a set API as existing on a sort of huge continuum from very abstract to very concrete. So at the very abstract end, we could think of a very mathematical view of a set with no specific representation, and we're choosing an item from the set is non-deterministic. You know, on thinking more concretely, we could think of something super concrete, like a C implementation of a set that uses hash tables, and where the select operation eagerly chooses whatever item happens to be first in memory. But for this demo, I'm going to consider two fairly closely related realizations of a set. An abstract model, where a set is represented as a list of integers, but selection is non-deterministic, and a concrete implementation that also represents a set as a list, but where select returns the first element. And using seek, I'm going to try and understand whether or not this concrete realization is a secure implementation of the abstraction. So to implement this in seek, I'm going to start by defining a BNF grammar of the set API language that defines programs as sequences of calls to the methods insert, remove, member, and select, and contexts as initial lists of integers for those programs to manipulate. We're then going to define the behavior of the source and target models as interpreters in a simple scheme-like language that's embedded in our Racket DSL. So here, I'm defining an abstract interpret function that dispatches on the requested method and calls a relevant function that implements the behavior at the source level. So for example, the abstract insert implementation is just going to add the given value to the start of the list and remove any subsequent occurrences in the list. Similarly, I can implement the abstract select function as pattern matching over the list and non-deterministically choosing an item to return using this non-det feature you can see in the if statement at the bottom. And the interpreter for the concrete implementation is going to look pretty similar. So its insert function is going to prepend a value to a list. And instead of having that non-deterministic selection, it's just going to return the first element in the list. And so this is the concrete implementation that I want to reason about the security of with respect to that abstract implementation. Once we've defined these interpreters, we can tell seek how the languages are related to each other. So the first two definitions on this slide describe how the grammar's non-terminals map to language expressions and contexts, how expressions and contexts should be linked together, and specify the relevant functions that implement their evaluation functions at each level of abstraction. The final definition on the slide links the two models together with a compiler and the relation between behaviors at the source and target level. So in this very simple case, the compiler is the simplest possible thing. It's just the identity function. And all of the differences in behavior between my source and target levels are going to come entirely from the different evaluation functions that I implemented. And now with these prerequisites all set up, we can start asking Seek for evidence of the insecurity in our concrete implementation. So the first level of evidence we're going to ask Seek to synthesize is a program and a context whose behavior changes when we compile them. More formally, we're going to ask Seek for a source level expression and a context whose behavior when linked is not the same as the target level behavior when linking their compiled forms. This query is captured in Seek by the find change component function. So when we run this, in this case, it's going to tell us that the sequence of operations insert -1, insert 5, and then select has different behavior in the concrete model, since in our abstract model, it can return either -1 or 5 non-deterministically, but in our implementation, it must return 5. And in this case, we're actually happy for our implementation to do this because it's a refinement of the specification that makes sense for the particular decisions we're trying to make. So we're going to ignore this counterexample for now. The second level of evidence we can ask Seek to synthesize is to find a program and a context that demonstrate a truly emergent computation. So some behavior that's possible in the low-level model, but not in the high-level model under any context. More formally, we're going to ask Seek to find a source-level expression and a target-level context such that there is no source-level context that has the same behavior when linked with the expression as the target-level context linked with a compiled expression. So in Seek, this query is called find weird components. And running it on our two models is going to report that inserting -8 twice, removing -8, and then selecting can return -8 in our implementation, but not in our abstract model. And based on everything I told you, this should be a really surprising behavior because we'd expect the set to be empty after removing -8 and the select to return false. So let's revisit our implementation and see what's going on here. You can recall that the concrete insert operation I described just appended a new item to the front of the list. And I cheated a little here because I didn't show you the implementation of remove for this implementation. So let's look at it now. And if you look at this very carefully, you're going to see that there's a subtle bug. Remove traverses the list until it finds an occurrence, the first occurrence of an element, drops it, and then it stops recurring. But after inserting, we could have an element appearing in the list more than once because we just prepended to the front of the list and didn't bother looking at what was already there. So we can mitigate this bug by continuing the recursion during remove, even after we've dropped the first occurrence. And now that we've fixed this bug, we can see if there's any more unexpected behaviors still lurking in our implementation. And luckily for us, in this case, Seek is going to report that there are no more weird behaviors in our implementation. And so we're faithfully implementing the abstraction as we desired. The third level of evidence we can ask Seek to synthesize is a program and a context that demonstrates specific target behaviors are present in our implementation. And this is actually a fairly standard program synthesis task, where we ask for a Gadget program that satisfies a specification on all inputs. So in this case, I'm going to ask Seek to synthesize an add one gadget that increases the length of the list, implementing the set by 1. If I provide this specification to the find gadget query with our buggy concrete implementation, it's going to report that we can implement this spec with a gadget insert 0. And what's interesting to note about this is that no such gadget would exist after we fix the bug that we just found in set remove, because there's no single element we can choose to insert that would be guaranteed to not already appear in the list. And so this is an interesting example of how the presence or absence of these emergent computations can really affect what an attacker is able to do when they're interacting with our system. And the final and most complex level of evidence of insecurity that Seek can provide is a collection of gadgets that can be composed with each other to implement complex behaviors. And this capability in Seek is designed to help system designers assess whether their designs enable really dangerous reusable gadgets, like those used in exploit techniques such as return-oriented programming. The formal definition of this query is similar to the find gadget query, except that it must simultaneously synthesize gadgets that satisfy a collection of specifications. And importantly, there must exist what we call a decoder gadget that ensures that each context is interpreted the same way by the specifications. And this mutual agreement is going to ensure that the gadgets can be composed arbitrarily. So in this case, I'm going to ask Seek to find us a decoder that interprets a set as a Boolean value, and a pair of gadgets that implement the identity and not Boolean operations. And Seek is going to come up with a decoder that says a set is true if it contains the member -6 and false otherwise. And then given this decoding of sets, it can tell me that the identity gadget is select, which has no effect on the set, and that the not gadget should remove -6 if it's present and otherwise insert it. So now that I've given a quick demonstration of Seek's capabilities and what it looks like to use the tool, I'm going to tell you about some of the case studies we conducted. Our first case study was focused on printf-oriented programming, which is an exploit technique that abuses formatted output capabilities in C to perform unexpected computations or read and write from arbitrary memory on the stack. And our goal in this case study was to demonstrate that Seek can synthesize example emergent computations that are really similar to the kinds of handcrafted weird machine gadgets that hackers develop. And we did this by synthesizing printf gadgets for a large range of Boolean operations and state updates. Our second case study focused on how Seek could be used to assist in the implementation of a high-level specification. So during this case study, we showed how Seek synthesized interesting behaviors arising from bugs in the implementation of the set API that I was just talking about, building even further on that implementation than what I showed here. And we also used this case study to test our theory and tools for reasoning about gadget composition. So I actually went beyond the example I just showed you to synthesize more interesting computational structures, including notably an algorithm for representing integers using sets that corresponds to conflict-free replicated data types that are used for counters in distributed systems. And it was really exciting to see how the synthesis capabilities in Seek were able to come up with such a complex algorithm. Our third case study focused on data-oriented programming, which is an exploit technique that reuses its host program to perform computations, but with the constraint that the control flow of the program can't be modified. And we chose this case study because language-level vulnerability classes, such as memory safety errors that are crucial to DOP, are something we see as a critical application area for Seek. And also because the emergent computations exploited by DOP are really specific to the particular host programs they target, presenting an interesting challenge for the tools. So we represented data-oriented programming in our framework by considering a compiler between two model languages, which we call TinyC and TinyA. TinyC is a C-like language with variables, pointers, and procedures, and its semantics enforces memory safety and explicitly makes memory errors invalid. And then to support interesting interactions, we added input and output commands that read and write memory at a pointer. TinyA is a model assembly language with unstructured control flow, no distinction between integers and pointers, and an input command that can write an unbounded number of bytes on the stack. So you should think of this like the insecure C function gets for reading input from a user. And then the compiler from TinyC to TinyA compiles the structured control flow to unstructured control flow and explicitly introduces things like allocations of stack frames. And an example of an emergent data-oriented programming computation that we were able to model is this small program, which takes as input a password, checks it against an argument to the program, and then prints out a secret value if they match. And it turns out this program has a vulnerability where supplying too much input to the program can overwrite the variables auth and secret on the stack. So using Seek, we were able to synthesize not just inputs that overwrite these variables, but specific data-oriented programming attacks that satisfy requirements, such as bypassing the program's authentication or overwriting the secret. And our final case study looked at how Seek could be used to assist in the design of a heap allocator. And this is a really interesting case study because there's been a long-standing arms race between allocator designers and hackers, where designers have to continuously devise new and interesting mitigations to eliminate sources of emergent behavior that hackers discover when exploiting systems in practice. And so our goal with this case study was to explore how iteratively querying Seek could help guide a designer to find a more secure solution without having to wait for a hacker to figure out the exploits first. So for this case study, our high-level model was an abstract specification of a heap allocator with support for malloc and free and reading and writing through pointers. And it had a notion of well-typed pointers that tracked their base and offset. And then the low-level model represented a concrete implemented heap allocator that had explicit free list management and inline metadata within the heap. And in this case, the compiler between the two was a refinement relation that captured when a concrete heap is equivalent to some abstract heap. And it needed to encode permissible sources of non-determinism, like the layout of objects within the heap and the order of blocks in the free list. So as part of this case study, we were able to synthesize a number of interesting attacks, including gadgets that do things like resize blocks or force allocations to happen at specific addresses. And the address forcing gadget was actually pretty interesting. It's fairly complex and took Seek over an hour to synthesize, even when we restricted it to considering a very small heap. But interestingly, using our intuition, we could decompose this operation into two simpler gadgets. One we call find head, which creates a dangling pointer to the head of the free list by allocating and deallocating a block. And a second called insert in free list, which overwrites the next pointer of an entry in the free list. And what's interesting about this is that synthesizing each of these gadgets takes only seconds. And this really shows the power and the danger of composition and the importance of reasoning about whether or not these sort of composable gadgets are admitted by a design. This was also an interesting case study for us because the iterative development process really did uncover some interesting corner cases that we hadn't imagined in advance. In this case, things like vulnerabilities related to dangling or forged pointers that we weren't thinking about when we started the case study, but sort of jumped out. So to wrap up, I want to discuss some of the high-level lessons we've taken from the project and where we're planning to go next. So our biggest takeaway is that having an oracle of the unexpected behaviors in your compiler or system is really valuable. So we were often surprised by the examples that Seek chose to show us. Our second major takeaway is a bit less positive. So while using Seek, we often found ourselves fighting with the scalability of the underlying tools, particularly when the symbolic execution engine encountered a state space explosion, which was particularly a problem when dealing with like a low-level assembly model. And often these issues we could work around, but they required really deep knowledge of what was going on under the hood of the tools. So we think that for larger systems, deductive symbolic execution and C just working alone might be too blunt of an instrument. We often resorted to exploring sketches of interesting scenarios that we came up with via intuition or fully concrete test inputs. And we expect that combining something like Seek with other approaches for exploring large state spaces, like fuzzing, might really boost the effectiveness of both. But that said, we definitely believe that exhaustively checking small models is a really great way to give high assurance about a design that can translate to meaningful guarantees about a large system, but of course only if your models are written carefully. So we're continuing to work on Seek and extending these ideas so that we can apply them to more realistic systems. And some of the new ideas we're excited to explore in the future are improving the synthesis capabilities of Seek by incorporating techniques that are really directly targeted at secure compilation, such as back translation, which we're going to hear more about later in the workshop, and extending Seek to more automatically search for those composable gadgets without requiring as much manual specification as we currently do to sort of have insight about what they might be. And so I'd just like to conclude by inviting you to try using Seek in your own projects. As I mentioned, it's on GitHub, and we'd be excited to hear if it's able to help you and to answer any questions you might have about us. And you can contact us using our email addresses, which are on the slide. So thanks for your attention.
Thank you, Scott. We have a first question from Marco, who was a victim of Hermite's restriction on the length of messages. So he first wrote this. An interesting recent application of weird machines is the idea behind the microarchitectural weird machines paper, where weird behaviors result from side effects and conflicts between microarchitectural entities such as branch prediction. And I don't know the rest. And then Marco's question is, how complex is building a Seek model for a specific setting? How do Seek's synthesis capabilities scale with the complexity of the underlying system model?
So I'll answer this question first, perhaps. So in general, building a model is, as a first stab, is pretty friendly, because you just need to implement, the kinds of operational semantics models that we're familiar of implementing for different programming language research projects. The real challenge is kind of what you hint at with the second part of this, is getting the synthesis capabilities to scale. And so underlying these tools, as I mentioned, we're using symbolic execution pretty heavily. So the sort of starting point to be able to get interesting results from the system is being able to craft your model in such a way that symbolic execution can effectively build you a small enough model with interesting features. And so we ended up having to play lots of tricks in our assembly models to try and make sure that we were getting state merging in the right place, just so that, coming up with an abstract model of the behavior of the program at one level was tractable. And so if you can manage that, the tools work pretty well, but managing that is no small feat in its own. And maybe Marco, if you can clarify where you were going with the first question, I'd be happy to respond.
Yeah. Yes. So maybe can you hear me?
Yep.
Okay. No. So the idea, the first question was about this microarchitectural weird machine paper, which was, I think, presented at ASPLOS last year now. And the idea there is that weird behaviors result from side effects and conflicts between microarchitectural resources. So I don't know, for instance, how instructions interact with caches or predictors or execution ports. And then they use these interactions to build weird behaviors, right? So I was wondering whether this kind of setting could be captured in...
Yes, it's actually one of the motivations we had in this work, was trying to think about what tools you could build to understand the sources of emergent computation and stuff. And one place that this does play out in our existing tools is that the examples that get synthesized are really, end up focused on the features of your model that lead to execution, the emergent execution. So particularly, if you're thinking about a language like C or something, what's neat that can pop out of a tool like this is, the collection of language features that seem necessary to cause an emergent behavior. And I would say, I think where your question goes that we haven't really gotten into much is, whether or not these tools could help you pull out, say, the parts of a compiler and implementation that lead to the emergent computation. Yeah, it was these two language features, but what about how I implemented them led to the issue? And that's something we don't have any good answers about yet, but it's definitely something we want to think about.
Okay, thanks.
All right, and we have one last question from Rob.
So, so what kind of ideas and techniques are we interested in drawing from back translation? So right now, the way our synthesis techniques work, I mentioned, is we're really relying on the sort of deductive synthesis capabilities built into Rosette. And you can think of that as sort of relying on the SMT area solver's natural search strategy to decide, what target level context should I try next to satisfy this SMT formula that would demonstrate the behavior that I care about. And that's we're sort of leaving it entirely up to the solver to figure out how it should explore the relative spaces at the source and target poles. But we know from our research on secure compilation that often we have a pretty good idea of what a source level context that might have similar behavior to a target level context would be. And so the idea here is to try and use similar ideas of back translation to guide the search procedure to say, when you're looking for a source level context that has the same behavior or different behavior than we witnessed and were concerned about, like, you should really focus on these sets of contexts that look like that are likely to succeed. And the hope is that by guiding the search in that way, we can much more quickly find interesting results.
All right. Well, thanks, Scott, and let's thank the speaker again.